So let's look at the existence and uniqueness of a solution. And let's suppose that we have a first order differential equation, and we're just going to describe it this way. That our first derivative is solved for dy dx, and that derivative is a function of x and y. We could have just x's over here, we could have x's and y's. And we have an initial condition, x sub 0 corresponds to some y sub 0. So one thing that we have to think about is that if this is a condition, if that's a point that our curve goes through, then we have to assume that that point actually exists. We can't have some solution that goes through a point that's not even there. We can't have it having a slope that's not even there, that we can't understand or quantify. So one thing we have to do is we have to show that there is a point, x sub 0, y sub 0, and not only is there that point, but that it exists inside a neighborhood. So if we go slightly to the left or slightly to the right of x sub 0, then points around it, its neighbors, also correspond to a solution of this differential equation. If the point x sub 0, y sub 0 is a singularity, if at that one specific point there is a solution, or let me say it this way, if at that specific point a function or the derivative is defined but points around it is not defined, remember when you're looking at derivatives and slopes, you have to have continuity. You can't have a derivative at a single point, because if we have a single point, we don't know, is the slope going that way? Is the slope going that way? Is it going that way? That way? Which way is the slope going? So we do have to have continuity. They put it a fancy way and say that this has to exist, has to be continuous in some rectangle containing points x, y, such that x is between some values a and b, and y is between some values c and d. So that means in the x direction, we go from somewhere to somewhere, and our x is in between those. And in the y direction, we have an interval that goes from somewhere to somewhere, and our y, that's our initial value, is in between those. So if we have a point that is in the interior of some rectangle, so essentially if at that point, if we're continuous, if points next to it, a little bit above it, a little bit below it, it's still defined, then that's what we're looking for. So we would check our function, whatever our dy dx equals to, and we would plug in our point to see, is it continuous for that particular function. But it has to not only be continuous for it, it also has to be continuous for the partial of that function with respect to y. So if those are continuous in if f and the partial of f with respect to y, if both of those are continuous at x sub 0, y sub 0, and points around it, then we say that there is a solution. There is a solution that exists, and it's unique. Which means if we consider, and again, we haven't really talked about slope fields yet, but You might remember talking about vector fields, slope fields, things like that from calculus. If we have one of those fields, that if you give me an initial point, some starting point, there's only going to be one solution curve. Remember, for a differential equation, if we, I'm just making some numbers up, if we integrate that, we're going to get that arbitrary constant on the end, which produces a family of solutions. So we have lots of families of solutions, but for a given point, there's only going to be one of these arbitrary curves that goes through that one point. So we can follow our slope field and find out what that arbitrary curve looks like. It could also be said that this family of curves, they don't intersect. How do I mean they don't intersect? If they intersected, that means for a single point, there could be this solution or they could be that solution. But that's not going to be the case. If we have given slope field defined by that particular differential, and we have some initial condition, as long as at that point where our function is continuous and the partial is continuous at that point, defined there and points next to it, then our solution is going to exist and it's going to be unique. There's not going to be one and then another curve that goes through that same point. So let's look at an example or two to see how are we going to show whether a particular problem has a solution that exists and is unique. So let's look at an example. Let's suppose we have dy dx, let's say 2 dy dx minus 4y squared equals 6x to the fourth. And let's look at the initial condition that y of 0 equals 2. So first of all, we need to find f of xy, which is what dy over dx is equal to. So if we isolate dy over dx, we're going to move 4y squared to the other side, and we're going to divide both sides by 2. So f of xy is 2y squared plus 3x to the fourth. And if we substitute in our initial condition that when x is 0, y is 2, so put a 2 in for y, put a 0 in for x, that's not undefined, that is defined. So it meets the first criteria that f of x of y is defined. And not only is it defined, notice if we were to pick x values to the left or to the right of 0, that would not change the fact that this is still going to be defined in values in any interval containing x equals 0. So then we need to check our partial. So we need to take the partial of this with respect to y. So if this is f of x of y, if we take the partial of that with respect to y, the first term gives us 4y. If we're taking the partial with respect to y, we treat all of this as a constant, so the derivative of that is 0. Notice if we substitute our initial condition in our x and our y into our partial, then in place of y, we put a 2. And that's still defined, that's still continuous. And likewise, that's going to be continuous at any x or y value, any x value left or right of 0, and any y value above or below 2. So since f of xy and the partial of f with respect to y, since both of those are defined and we're continuous at that point, then we're guaranteed that there is some solution. The solution exists, and that it's a unique solution. So no, not only is there some equation that has this characteristic that twice the first derivative minus 4 times the equation squared equals 6x to the fourth. Not only does it exist, but given that initial value, there's only one curve that goes through that point. So let's look at another. Let's take a look at this one. dy over dx equals 3x minus the cube root of y minus 1. And when x is 2, y equals 1. So, first of all, f of x comma y, that's our function that equals our first derivative. And if we substitute in 2 for x and 1 for y, we get 3 times 2 minus the cube root of 1 minus 1. So 6 minus the cube root of 0. The cube root of 0 is 0. 6 minus 0 is 6. So this point is defined at in our first derivative. We're going to plug that in. Now, let's think about, is that point in some rectangle that is defined that this is continuous for? So, if we go a little bit to, no, that's not to scale, but if we go a little bit to the left of 2 or a little bit to the right of 2, a little bit above 1 or a little bit below 1, is that still going to be defined? Well, for this one, yes, it is, because looking at our equation, if I put values less than 2 or greater than 2, that's not a problem. That's not going to be undefined. And since this is a cube root, we can take the cube root of any kind of number, positives or negatives. So even if we have a y value that is a little bit less than 1, such that this comes out to be negative, that's not a problem because we're taking the cube root. But if that was a square root instead of a cube root, then notice a y value of 1 would give us a square root of 0, which is on the boundary of that range. There are no y values smaller than 1 for which that's defined. So that point would not be on the interior. That point would be at the edge of a rectangle that contains that point. So that's one way that the f can be defined at a point, but it's not inside the rectangle, it's on the edge of it. So let's go back and finish working our problem instead of the other example. So it passes that for this function, for our dy dx, that point is continuous in some rectangle. So now let's check our partial of f with respect to y. So if we take the derivative of this with respect to y, the derivative of the first term is just 0. Let's rewrite the cube root as y minus 1 to the 1/3 power. So if we take the derivative of that, the chain rule says bring down the 1/3. Do that to the 1 less power times the derivative of the inside. We're taking the derivative with respect to y, so that's 1. So we end up with negative 1 over 3 times the cube root of y minus 1, and all of that squared, or we could put the square on the inside. So that's our, that's our partial with respect to y. Now notice for our point 2, 1, this is going to be undefined. If we substitute a 1 in for y, we get a 0 on bottom. So the partial of f with respect to y is not continuous. So since that point is not continuous, if it's not continuous at that point, then there's not going to be any rectangle that the whole rectangle is continuous either. So since it's not continuous at that point, then this theorem does not guarantee existence and uniqueness. So let's be careful what that doesn't say. So what if f of x of y and or the partial of f with respect to y, what if they fail continuity at the initial condition? Remember when we have if-then statements, if the first one is true, then the second one is true. It does not mean that if the first one is not true, then the second one is not true. That's not guaranteed. If the first one is not true, that just means we don't know what's going to happen. So it failed that the partial of f with respect to y was continuous at our initial condition. So what does that mean? It means we don't know if there's going to be a solution. And if there is a solution, we don't know if it's unique. So if it passes the 2 test, then there is a solution and it is unique. But if it fails the test, we don't know. There could be multiple solutions, or there could be no solutions. So we would just have to progress and see what we could find out.